Hi, my name is John Gulbranson and I'm the president of International Test Instruments. In this presentation I will talk about the history of PC buses from ISA to PCI Express. So it all started back in 1981 when IBM created the original IBM PC. That machine used a Intel 8088 CPU running at 4.77 megahertz, which resulted in the blazingly fast I/O bandwidth of 4 megabytes per second. The ISA standard, however, was created a few years later in 1984 when the PC-80, the improved PC, was created, which used the 8286 CPU. And that CPU uses a 16-bit data bus running at 8 megahertz for a total memory and I/O card bandwidth of 60 megabytes per second. There are two versions of the ISA card. The original 8-bit, which was used for the 8088 or original IBM PC. And you also have the 16-bit extended cards from the PC-80, which is technically only the ISA bus. The original one is not technically part of the ISA standard. Only the 16-bit one is actually spelled out in the standard, but commonly we call both of those card versions the ISA card. So depending on the actual CPU used, the 8088 or the 286, you can address either 1 meg or 16 meg of address range on the CPU bus and therefore also on the I/O card. Both of these CPUs support 64K of address space. One of the problems, of course, is that the ISA bus is not very fast. It was an old design from 1980, essentially, and after about 10 years, when Windows came along and other GUI-based operating systems, the I/O bandwidth was not enough to support the advanced graphics cards that started to come along. So the graphic cards manufacturers came together and through their group, the VESA group, Video Electronic Standards Association, created a VL bus or VESA local bus, which essentially was again a direct attachment of the graphics card and any other card, I/O card that you wanted to directly connect with high performance, and they connected it to the CPU memory bus again. And because the top of the line CPU at the time was the 486 CPU running at 33 megahertz, that was the bus standard for the VL local bus. And the problem, of course, with doing that is that they married it to the 486 CPU bus protocol, and when other CPUs came out, particularly the Pentium, it used a different bus protocol, and the VL bus was no longer an option. It simply didn't work. Later on, IBM tried to create a future-proof and CPU-independent alternative to the ISA bus as part of their MCA microchannel architecture design. And we'll talk about that bus and the VL bus in some future slides. This slide shows the original IBM PC-80 motherboard from 1984. This is the board that uses a 8286 CPU. And you can here see the two different slots. This is the legacy original PC slot, and this is the extended, you see the extension here, connector for the actual ISA slot, which is part of the ISA standard from 1984. So technically this is the only true ISA slot, but we refer to both as ISA slots and therefore ISA boards. So in this slide behind me here, you see the pinout of the ISA bus connector. This is the hold connector for the that is spec'd as part of the 286 computer, and this part here is the original PC connector, the 8-bit. You have 8 data bits on this connector, and you have another 8 on this. So in total, you have 16 for the whole interface.
PCI Express. Einige werden sich jetzt fragen, warum erklärt ihr mir eine 10 Jahre alte Schnittstelle? Aber Tatsache ist, PCI Express war lange Zeit für viele Leute einfach nur der Slot, wo man die Grafikkarte reinsteckt. Und die Details haben eigentlich gar nicht so interessiert. Erst in den letzten Jahren, wo immer mehr PCI Express Geräte und Erweiterungsmöglichkeiten auf den Mainboards Einzug halten, wird es eigentlich immer wichtiger, was diese Schnittstelle eigentlich alles kann und macht. Und auch meine Mainboard-Reviews konzentrieren sich immer mehr darauf, welche Erweiterungsmöglichkeiten eigentlich über PCI Express geboten werden. Und viele Leser haben mich gefragt, was ist das eigentlich? Was ist eine PCI Express LAN? Was kann die? Wofür ist die da? Und deswegen versuche ich das heute nochmal ein bisschen zusammenzufassen. Erstmal als Kontrastprogramm, was PCI Express nicht ist, nämlich der Vorgänger PCI. Wir hatten bis vor 10 Jahren die primäre Schnittstelle für Erweiterungskarten. Seitdem versucht PCI Express das abzulösen, klappt aber immer noch nicht so ganz. Selbst für Skylake erscheinen wieder Mainboards, wo auch PCI drauf ist. Aber ich habe hier mal ein ganz altes mitgebracht, um das so ein bisschen zu verdeutlichen. Die Besonderheit bei PCI war, alle Slots hingen an einem gemeinsamen Bus und es waren auch relativ große Slots mit vielen parallelen Datenleitungen. Das heißt, wir haben hier 32 Datenleitungen, die gehen einmal komplett durch und jeder Slot hängt dran. Das war recht praktisch, weil man die Leistung auf beliebige Karten verteilen konnte. Nur war die Leistung irgendwann zu wenig und man konnte sie kaum steigern. Denn mit 32 parallelen Datenleitungen hat man das Problem, wenn die nicht alle genau gleich lang sind, genau gleich arbeiten, kommt am Ende nur noch Blödsinn raus. Die einzelnen Bits kommen nicht zum gleichen Zeitpunkt an über die vielen unterschiedlichen Wege und das Ganze macht das Mainboard-Layout sehr komplex. Deswegen hat man für den Nachfolger PCI Express ein komplett anderes Modell gewählt. In Hardware haben die beiden eigentlich gar nichts gemeinsam. Der Name ist zwar noch gleich und auch das Ansprechverhalten der Karten durch das Betriebssystem ist gleich. Das heißt, man musste Windows nicht umgestalten, um die neue Schnittstelle einzuführen. Aber mechanisch und elektrisch sind die komplett anders aufgebaut. Man sieht das hier schon so, die klassischen PCI Express Slots, die meisten werden es kennen, gibt es zum Beispiel in unterschiedlichen Längen. Und das ist schon erst ein Hinweis darauf für das Grundkonzept, denn PCI Express arbeitet mit sogenannten Lanes. Wir haben nicht mehr einen Bus, wo ganz viele Datenleitungen versuchen parallel zu arbeiten, sondern wir haben eine einzelne Einheit, die nur aus einer Datenleitung vom PCI-Controller, zum Beispiel in der CPU, zum PCI-Endgerät, zum Beispiel auf der Steckkarte führt und eine zweite Datenleitung für den Datenverkehr in Gegenrichtung. Und diese beiden Leitungen arbeiten als eine Einheit, haben ihr eigenes Taktsignal und können sich nicht irgendwie gegenseitig stören, weil es ist halt nur eine Datenleitung, auf die die Daten hintereinander sequenziell kommen, statt dass man parallel mehrere Datenleitungen koordinieren muss. Wenn man bei PCI Express die Bandbreite aber über das Maß einer Lane hinaus steigern möchte, hat man auch die Möglichkeit, mehrere Lanes in einem Slot zusammenzufassen. Das heißt, wir haben hier zum Beispiel einen X4-Slot, hier einen X16-Slot, das ist der, den man typischerweise für Grafikkarten nutzt. Der ist logischerweise bei gleichem PCI Express Standard 16 mal so schnell wie der X1. Und auch hier ist das nicht etwa eine große parallele Schnittstelle, sondern wir haben hier wirklich 16 unabhängige Systeme zur Datenübertragung. Und wenn das eine mal ein bisschen anders arbeitet als die anderen, dann stört das nicht. Denn die Daten werden über jedes einzelne Lane als Pakete übertragen und erst die Pakete werden am Ende in der GPU wieder zusammengesetzt. Und dabei ist eigentlich vollkommen unabhängig, in welcher Reihenfolge die eingetroffen sind, solange sie jetzt nicht, ich sag mal, wirklich lange verzögert und zu spät kommen. Aber die genaue Timing ist nicht mehr wichtig und man hat somit wesentlich mehr Möglichkeiten, die Leiterbahnen über das Mainboard zu führen. Die können auch mal ein bisschen unterschiedlich lang sein. Ein weiterer Vorteil dieser Lane-Bauweise sieht man schon, wenn man sich die Slots mal genauer anguckt. Und zwar fängt jeder PCI Express Slot ähnlich an. Wir haben hier diese etwas längere Kerbe, dann beginnt die kurze. Bei den großen Slots geht es dann halt einfach länger weiter. Aber der erste Abschnitt eines X16-Slots sieht genauso aus wie der X1-Slot. Und das ist auch absichtlich, denn man kann jede PCI Express-Karte auch in größeren Slots betreiben. Ich kann hier zum Beispiel meine X1-Karte auch nehmen und sie in den X16 stecken, wenn ich einen davon zu viel hatte. Und sie wird da genauso arbeiten wie in einem X1-Slot. Wesentlich flexibler, was die Nutzung von Slots also angeht. Es geht sogar umgekehrt. Einige Mainboard-Hersteller verbauen PCI Express Slots, die nach hinten offen sind. Das heißt, ich kann jetzt hier in einen mechanischen X4-Slot eine X16-Grafikkarte reinstecken. Und wie man vielleicht sieht, die Kontaktleiste der Grafikkarte ragt einfach nach hinten aus dem Slot heraus. Das heißt, sie kann 12 von ihren 16 Lanes gar nicht nutzen. Aber mit den ersten 4 wird sie genauso arbeiten wie sonst auch. Ein bisschen langsamer. Aber das Protokoll sieht vor, dass die Karten auch mit weniger Lanes zurechtkommen müssen. Also alles einfach und flexibel und super toll mit PCI Express. Dann würde ich jetzt garantiert kein Video drüber machen. Es kommen nämlich weitere Komplikationen hinzu. Genauso wie ich eine X16-Karte in einem X4-Slot betreiben kann, wenn sie mechanisch da reinpasst, oder eine X1-Karte in einem X16-Slot, spricht nämlich auch gar nichts dagegen, einen mechanischen X16-Slot mit deutlich weniger als 16 Lanes anzubinden. Und da kommen wir jetzt nämlich zu dem Dauerthema PCI Express Sharing und Umleitung von Lanes, um an irgendeiner anderen Stelle andere Hardware anzubinden. Ein aktuelles Beispiel habe ich euch mal mitgebracht. Ein brandneues Skylake Mainboard. Wer die Berichterstattung über die CPUs mitverfolgt hat, wird gehört haben, dass in der CPU ein PCI Express 3.0 Controller mit 16 Lanes sitzt. Wer sich dieses Board nun genauer anguckt, dem fallen 3 optisch hervorgehobene mechanische X16-Slots auf und die sind entsprechend der Folgen tatsächlich auch alle über die CPU angebunden. Wenn man jetzt kurz nachrechnet, 3x16 auf 1x16, das geht nicht auf. Und das ist typisch für moderne Mainboards. Und man kann immer sehr schön daran notieren, wenn man irgendwo diese rechteckigen Chips sieht, in dieser typischen, sehr regelmäßigen Anordnung, dann hat man quasi immer PCI Express Sharing auf dem Board. In diesem Fall sind 8 der 16 CPU-Lanes permanent mit der ersten Hälfte des obersten Slots verbunden. Die anderen 8 Lanes gehen aber erstmal zu diesen, ich nenne sie immer PCI Express Splitter. Und die haben die Möglichkeit, zwei ankommende Lanes je Chip in 2 verschiedene Richtungen weiterzuleiten. Entweder ebenfalls zum ersten Slot, dann erhält er alle 16 Lanes, oder aber sie leiten die 8 Lanes, die zu diesen 24 gehen, zum zweiten Slot weiter. Dann haben wir hier also hier nur 8, aber hier auch 8 Lanes. Normalerweise kriegt der zweite gar keine. Der Trick dabei ist, das Ganze wird einmal beim Einschalten des Systems festgelegt. Das heißt, sobald ich eine Karte in diesem Slot hier montiert habe, selbst wenn sie gerade gar nichts zu tun hat, kriegt die erste Karte, meistens die Grafikkarte, immer nur 8 Lanes ab. In diesem Fall geht es sogar noch weiter. Sitzen nochmal 2 dieser schönen Chips. Die können von den 8 Lanes, die in diesem Slot weitergeleitet wurden, 4 Stück nehmen und noch einmal an diesen weiterleiten. Das heißt, obwohl dieses Mainboard garantiert von einigen Händlern mit 3x16 beworben wird, ist es eigentlich ein 8-4-4-Board. Einen kleinen Sonderfall des CPU-Lane-Sharings möchte ich an der Stelle auch erwähnen, weil er gerade auf besonders teuren Board anzutreffen ist. Und zwar gibt es nämlich einen Trick, sogenannte PCI Express Switch. Manchmal werden auch diese Umschalter, die ich gerade schon vorgestellt habe, als Switch bezeichnet. Der Begriff Schalter ist da im Englischen leider nicht ganz deutlich. Was ich hier meine, ist ein Switch im gleichen Sinne, wie es auch zum Beispiel bei Netzwerk-Switch verwendet wird. Das sind spezielle Chips, die nehmen die Lanes, die zum Beispiel von der CPU kommen, und bereiten diese intern auf. Das heißt, eigentlich ist der Chip mit 16 Lanes in diesem Fall an die CPU angebunden. Dieser Chip hat seinerseits 32 weitere Lanes, mit denen er andere Geräte anbinden kann. Bei derartigen Boards ist es also tatsächlich möglich, dass 2 Grafikkarten parallel mit 16 Lanes arbeiten und die können auch beide mit voller 16-Lane-Geschwindigkeit mit der CPU kommunizieren, nur halt nicht unbedingt zeitgleich. Es sei denn, es müssen zufällig genau die gleichen Daten von der CPU zu den Grafikkarten übertragen werden. Alternativ können sie auch untereinander mit der vollen Geschwindigkeit kommunizieren, ohne dass die CPU überhaupt belastet wird. Derartige Switches sind also eine Möglichkeit, die Leistung durchaus ein bisschen über das zu steigern, was die CPU selbst kann, und werden deswegen vor allem auf sehr teure Mainboards verbaut. Ich zeige das auch nochmal auf der Rückseite. Das kann man hier mit etwas Glück erkennen. Man hat hier also wirklich die Leiterbahnen, die von der CPU kommen. Die enden hier in diesem Bereich. Und von hier aus gehen deutlich mehr Leiterbahnen wieder los und zu den Lötkontakten der einzelnen Slots. Die gerade angesprochene Verteilung der CPU-Lanes mag jetzt einigen Leuten schon komplex erscheinen, aber eigentlich ist es relativ übersichtlich. Es gibt auf den meisten Boards die Möglichkeit, Lanes an weitere Slots umzuleiten. Auf einigen Boards gibt es halt noch die beschriebenen PCI Express Switch, die für effektiv mehr Lanes seitens der Endgeräte sorgen, als die CPU eigentlich bereitstellen kann. Das kann man in den Spezifikationen meistens ganz gut nachlesen. Unübersichtlich wird es nur bei der Sockel 2011 V3-Plattform, schlichtweg weil Intel da eine CPU anbietet, die weniger Lanes zur Verfügung stellt als die Top-Modelle der Plattform. Und das sorgt halt dafür, dass es alle Bandbreitenangaben in zweifacher Ausführung gibt, je nachdem, welche Chip man verbaut hat. Wirklich kompliziert wird es aber bei der zweiten Quelle von PCI-Express-Lanes auf modernen Mainboards. Und zwar hat nämlich auch der Chipsatz, der heutzutage nur aus einem Chip besteht und bei Intel PCH heißt, bei AMD FCH, ein PCI-Express-Controller eingebaut. Und der wird nicht nur genutzt, um Erweiterungsslots anzubinden, sondern auch diverse Zusatzcontroller. Zusätzliche SATA-Ports, USB 3.1, zum Teil auch zusätzliche 3.0 Ports, wie gehabt schon X1-Slots, X4-Slots und manchmal auch noch diverse weitere Sachen. Natürlich bei der neuen Generation sehr beliebt der M2-Port für schnelle SSDs. Da gibt es vielfältige Möglichkeiten. Auch Netzwerk oder einige Audiochips werden über PCI Express angebunden. Es sind also sehr, sehr viele Endgeräte, die in Frage kommen. Und diese Chipsätze haben auch nicht wirklich viele Lanes.
The computer currently has one IDE hard drive. This is connected to the primary IDE controller. It also has a single optical drive which is connected to the secondary IDE controller. I'm going to be adding a second IDE hard drive, and I'm going to add it as a slave device to the primary controller. I will be removing the original hard drive so I can show you what the hard drive looks like, and then also so we can reconfigure the jumpers. First I'll begin by removing the power lead, gripped onto the Molex connector, and then I pull it out of the device. Then I remove the ribbon cable. I grab the ribbon cable close to the connector and then pull straight out from the device. Each computer case manufacturer holds hard drives into the case differently. Some computer cases use a quick release rails. These will snap onto the hard drive so they slide into the case. Others will have a plastic or a metal removable cage that holds the hard drive in. This one happens to have a fixed cage. This is welded right to the case, and then it uses screws to hold the drive in place. I'll remove these screws so then I can slide the drive out of the case. With the screws removed, I can carefully move all the components out of the way and then slide the drive out of the case. Here's the IDE drive that I removed from the computer. Here we have the 4-pin Molex power connector. We have our 40-pin IDE controller. Has a keyed notch here so our data cable can only fit in one direction. And then our IDE device has jumper settings. Somewhere on the IDE drive there will be a legend or some indicators to indicate which jumper setting will specify the device as a slave or a master device or a cable select device. In this case, if we remove all jumpers, that would be a slave device. If we set the jumper to the far right, that would be a master or single drive. Or if we set it on the third jumper, that will indicate or enable the cable select feature. This device is going to be our master device. So we're going to set it as the far right jumper. So this white jumper right here is already in the proper location. So this device will be the master device. We're going to install this on the primary controller. This device is going to be our slave hard drive. We're going to add this to the primary controller. This device doesn't happen to have a legend on top, but if I turn it over, the bottom jumper settings are listed right on the board. So here we have CS. If we were going to have a cable select device, we would use the first jumper. If we were going to specify this as a slave device, we would use the second jumper, and then the master device would be the third jumper. In this case, this is going to be our slave device. We will move it over to the second jumper. So this device is now configured as our slave device. IDE devices support one of two settings. We can either set all devices as the master or slave device, or we can set both devices as cable select. If we use cable select technology, we're going to have to use a cable select supported cable. Here's an example of a cable select supported cable. A couple of items on a cable select cable. One of them will have a little notch out of it. So in this case, we have one of the wires has been punched out. We also have markers on the connectors to indicate which connector goes to which device. In this case, this one says sys board, so this plugs into the motherboard. The connector at the end of this cable supports drive 0, so we would put our drive 0 or our master device on the end of the cable. And then drive 1 or our slave device would go on the center connector. So if we're using cable select, we have to use a cable select cable. Some IDE cables, like this one, are what are called 40-wire cables. So there's 40 wires and a 40-pin connector. These are used for optical drives and legacy hard drives that only support ATA33 or less speeds. Newer drives that are ATA 66, 100, or 133, need to use an 80-wire cable. These still have a 40-pin connector, but they have twice as many wires to support faster speeds. You can use a 40-pin cable with an ATA 66, 100, or 133 device, but it won't run at the fastest speed. So it's recommended to use these cables, the 40-wire cables, only for optical drives, and the 80-wire cable for any newer hard drives. Remove the ribbon cables from the motherboard so we can get a good look at them. Under each of these IDE controllers, we can see that this one says primary and this one says secondary. So we're going to connect our master and slave hard drives to the primary controller, and then our single optical drive will be on its own cable connected to the secondary controller. Whenever possible, you should separate hard drives and optical drives on separate controllers. In this case, we're going to put our hard drives on the primary controller and our optical drive on the secondary controller. You should also put your bootable drive that holds the operating system, you should configure that as the master device on the primary chain, and then any other hard drives or secondary hard drives should be configured as the slave device on the primary chain. Currently, our single optical drive is connected to the secondary controller. This cable is connected to our primary controller. This is what will attach our master and our slave hard drive. This is going to be our master device. We've got the jumper set correctly, so this is the master. Carefully insert this into the computer case and then install the case screws to hold it in place. Installed and fastened the case screws. Now I can connect the data ribbon cable. Generally, you want the master device hooked to the end connector on the ribbon cable. This is our master device, so I'll connect the ribbon cable. And at this time I can also connect the power connector. Now I can install our slave device. This is our slave device. We've got the jumper settings set as slave, so I can carefully slide this into the computer case and then fasten the case screws. The hard drive screws are fastened. Now I can connect the secondary connector to our slave device. And then the second power connector. Here's a close-up to our setup. Here's our master device connected to the end of the cable. We have power connected. And then the secondary connector is connected to our slave device. This one also has power. And this cable is connected to our primary controller. With the hard drives installed, I can connect my monitor, keyboard, and mouse, power up the computer, and make sure that both drives are detected. Press the power button and boot the computer. As it boots, I can look at the BIOS splash screen, see if there's any indication that it found any devices. Press the pause break key to pause it. Here it indicates that it found a primary master device. It also found a primary slave device, and then a secondary master device. The delete key to enter the CMOS setup utility. Then I'll go into the standard CMOS features, and here we can see our current IDE setup. You can see our primary master device was auto-detected. It's a 40,000 megabyte or a 40 gig drive. Our primary slave device was auto-detected. It's a 19,996 megabyte or a 20 gigabyte hard drive. And then our IDE secondary master is an MSI CDRW. That's our optical drive. Looking at both the BIOS and the CMOS, it appears that the jumpers were set correctly and all devices were properly identified. So from here, we could save our settings, the computer would restart, and then we could go into whatever operating system we're using, and now we would partition and format our hard drive to be able to use it.
The abbreviation SCSI is pronounced SCSI, and this stands for Small Computer Systems Interface. It was a method of connecting storage devices in, at that time, were small computer systems or personal computers, and it was one of the very first ways that we had standardized storage on our computer systems. We were able to do quite a bit with this. We could string a number of devices together. They could be hard drives, they could be optical storage devices, and we could put up to 16 devices on one of these SCSI chains using a single cable and a single SCSI controller. So you were able to just put one interface in your computer and simply hang off the back of that interface 16 different devices. Through the years, there have been a number of different kinds of SCSI formats. You may see it called fast SCSI, ultra SCSI, there's ultra wide SCSI, there's ultra 2 SCSI, and so on. All of these formats tend to be backwards compatible, but the best possible performance you're going to be would be to get a storage device and a controller that were using the same type of SCSI interface. Before USB came along, SCSI was really the standard for connecting our peripherals together. We would plug in printers, scanners, tape drives, CD-ROM drives, anything that needed an external connection. SCSI was the format that we were using. On these SCSI buses, we had different sizes. We had a narrow bus SCSI. Some SCSI was a wide bus. The narrow bus could plug in 8 devices that we could string onto an individual controller. The wide bus allowed us to have 16 different devices on a single controller. The part of SCSI that really makes it powerful is that the interface and the communication itself is very, very intelligent. It's very powerful. We're able to do a lot of different communication over that SCSI bus, and it was very simple to plug in. Even though we were able to control so many diverse kinds of devices, it was a single type of interface. We assign a number to it, and now we've got a SCSI connection on our computer. SCSI has been around for a very, very long time. But even today, especially in large server farms, we see SCSI interfaces for hard drive controllers, and especially on virtualized environments, we see a lot of SCSI being used. Even though it's not a physical SCSI connection, we're still using that SCSI standard of protocols to communicate over these virtualized systems. One particular piece of SCSI that was very important, especially early on in SCSI, was the termination. You could plug many devices in, but the last device had to have what we called a terminator on the end of the chain. That way, the SCSI communication knew exactly where the signal ended. Without a terminator, none of these devices would be able to operate properly. The newer SCSI devices tend to have these terminators built into the device, and you can enable or disable the terminator just by clicking a button. But the older devices needed a physical terminator that you would connect to the interface that was on back of the SCSI device. There are many different types of interfaces that you'll see for SCSI. They've changed quite a bit through the years. Here's an example of one. You can see this one happens to be an Ultra 3 SCSI connection, and you can see a PATA connection right next to it. They're almost the same size. The SCSI might be a little bit shorter. This is a view from above. If we were to look at it from the side, you can see the interface connector is a little bit different than the PATA or the SATA connections that we've used before. This SCSI connection has quite a number of pins associated with it. The cable that we would use to connect this would be something like this, where we would plug into the motherboard, and then there might be many different connections on that same cable where we could use all of these different SCSI devices and plug them all in at the same time. If we were to look closer, you can really see a lot of different pins being used. And on this particular SCSI connection, it was a higher bandwidth, so it needed a lot more pins to be able to communicate. But it may not be this type of connection that you would see with SCSI. Because they've changed so much through the years, you might see a DB25 connection that looks like a serial, or maybe even an older parallel connection. They all look very similar, but these are actually SCSI connections. You have to look very carefully to see the differences. Some connections are very clear that they're SCSI. This high-density 50-pin connection has locks on the side of it that connect in. That's very, very exclusive to SCSI. And some of these higher density connections as well really make you see that very quickly that's a SCSI connection. There's nothing else that looks quite like those connectors. When you're physically connecting SCSI devices to the SCSI cable that you have, whether they are inside of a computer or outside of a computer, you have to give each one of them a completely unique number. This is called a SCSI ID. So on that single bus, on that single connection coming out of an interface of a computer, we would provide different IDs. For instance, if this was your boot disk, maybe we'll give that SCSI ID 0. If there's a floppy disk or a scanner or an optical device, we might assign that a number 2. If there's a CD-ROM, we might assign that with a SCSI ID of 3. There's also a concept within SCSI connections called a logical unit. So within each physical SCSI ID on that interface, you might have logical units inside of this. This was very common to see if you were plugging in an external SCSI storage device that had multiple hard drives inside of it. You would give the storage device itself a SCSI ID, and then there would be logical units assigned to the individual drives within that single physical device. You also see this quite a bit when you're working with virtualized systems. As I mentioned earlier, the signal that is at the very end of the SCSI bus has to be terminated. There might be a physical terminator, or it might be a termination functionality that's built into the hardware itself. If you ever see what we call SCSI attached devices that are serial attached SCSI, they don't have jumpers, they don't have terminators, they don't have settings. A lot of the more modern storage devices that we are plugging in over something called serial attached SCSI are completely automated in the way that they configure themselves on that SCSI bus. Here's an example of a legacy SCSI device. I think this is an optical device, but it could be a hard drive, it could be a scanner, it could be anything else. Generally, we see two different types of connectors on the back of the device. One of them generally is the connection going in. You can see it written on the back of the device, where we would plug in the in connection from our computer. If we had additional SCSI devices, we would use this out connection to keep the string going, to keep that daisy chain going throughout the connection. If this was the end of the line, if this really was the last device in this SCSI chain, this is where we would plug in the terminator. If this was a device that had the termination built in, there would probably be a connector on this device, or a button you could push to say this was the terminating place. And you can also see the SCSI ID number built right into this as well. There's little buttons that would allow you to change that SCSI ID. So when this device plugged in and communicated across the SCSI bus, everyone know that this device was SCSI ID number 6. Once you have everything plugged in, it looks a little like this, where you have a SCSI controller that might be ID 0. Here's SCSI ID 1, that's a hard disk. Here's another hard disk, and they're all chained together with different SCSI IDs, and at the end of the chain is a terminator. Usually these terminators even have a little light so you can see that they are active. Here's a picture of what a SCSI terminator might look like, so you can look at the back of your devices and see if you have one of those. That term daisy chain actually came from this idea of taking daisies and connecting them to each other, and you could wear them as bracelets or wear them on your head, and that same daisy chaining was how we came up with this idea of plugging in all of these devices one to the other to create that chain of devices. The back of the SCSI drive looks very similar to the back of any other hard drive. It's just using a very specialized SCSI connection on the back. Usually you have jumpers that can help you designate what the SCSI ID of this drive happens to be. And here's traditional power that you might find so that that drive can be powered up on the inside of your computer. This was an external device, then you have external power. You usually have options for setting your SCSI IDs that we saw on the SCSI device earlier, and the interfaces for going in and out of that SCSI connection. The connection of the SCSI device on your motherboard looks very similar to PATA in that we've got a connection on the motherboard and multiple interfaces on SCSI. But of course, with PATA, we are limited to 2 individual devices, whereas with SCSI, especially the wide bus SCSI, I can connect up to 16 devices, and you would simply find the closest connector to you and plug it in. It doesn't matter where along this particular cable we plug in our SCSI device. The determination of how this device communicates is associated with the ID that you assign to the SCSI device. So you simply plug into the closest connector to you and plug in all of your different SCSI devices, make sure they have different SCSI IDs, and your SCSI communication is now complete. Once you follow those rules, SCSI is very simple to get running, and it's going to provide you with a lot of flexibility to plug in multiple storage devices. If you're working with a relatively new computer, then it most likely is using SATA connections to plug in the storage devices inside of that computer. Here's an example of one of those. This is a 256 gig solid state drive that is using SATA connections to be able to communicate. And we'll look closer at what that might look like. SATA stands for Serial AT Attachment, that AT attachment being that older AT computer, one of the original style computers, and we've kept the terminology through the years. Although the original computers are well beyond us, we have this serial AT attachment to have some comparison back to the older parallel AT attachment, or PATA. We have different standards for SATA. One of the original SATA versions was version 1.0. It ran at 1.5 gigabits per second. There's also another standard, which is the SATA revision 2.0, which is running at 3.0 gigabits per second. The latest SATA standard goes even faster than that. That's SATA revision 3.0 that runs at 6 gigabits per second. One thing you have to watch for is occasionally you will see people abbreviate 3 gigabits per second as 3G. We can sometimes confuse 3G with third generation. That's not really the case. I've been very careful here to show you SATA revision 1, SATA revision 2, and SATA revision 3, and then the speeds of those being 1.5 gigabits per second, 3 gigabits per second, and 6 gigabits per second. So if you're looking at standards for SATA, make sure you don't confuse any of that terminology. It can become confusing when you're dealing with different versions and different speeds, but as long as you synchronize those up, you shouldn't have a problem. One of the advantages that SATA brings to the table is that the connections are much smaller on the motherboard. You can see one of the older IDE or PATA connections on this motherboard, and this motherboard also has SATA connections, 1, 2, 3, 4, 5, 6 different SATA connections. If you were to look at these cables side by side, you'd really see the difference. PATA uses these larger ribbon connections. Here's the SATA connections, a much smaller connector on the motherboard and a much smaller cable that's being used to the storage device. So for the purposes of managing cables inside of your computer and making sure that the airflow is maintained through your computer, SATA has some distinct advantages. This is the back of a SATA drive, very similar to the PATA in that your interfaces are on this side. It's actually this very small interface is the SATA data connection. This larger interface is actually the power for SATA. You've also got these jumpers, and then you have an older traditional power connection. This drive was built for a computer that may be transitioning between PATA and SATA, and they gave you the option you could either plug in with the newer SATA power, or you could plug in with the older 4-pin Molex connector onto this drive. You would only choose one of those. You wouldn't need to plug both of those in. One of the advantages with SATA, however, is there's the capability on a number of drives to do hot swapping. You could unplug this drive while your system was powered up and plug it back in. That would be something you would not commonly do, and you would certainly want to take proper precautions when you were doing something like that, but it is part of the SATA standard. If we were to look at the top of the drive itself, it would give us that documentation of what we just saw with the power on one side, our serial connection, which is the data connection to our motherboard, the jumpers that are on the side, and there's a legacy power connection built in right into the documentation on the top of the drive. If your power supply had some of the newer SATA connections, you would simply plug the power connection into the SATA power, and you would plug your data cable into the SATA connector on the drive. If you have an older power supply, then you would plug it in very much like this picture shows, where you still have the same data connection, but you would use this legacy Molex power connector to make sure the drive was operational.
The CPU, short for Central Processing Unit, is like the brain of the computer, and once you understand how it works, you'll understand the computer as well. Let's remove the cover of the CPU and zoom in to see what happens inside. There are lots of different wires carrying information around the CPU. This particular CPU is called the 6502 and was used in computers like the Apple II and the Commodore 64, as well as in the original Nintendo Entertainment System. This simulation of the 6502 can be found online at visual6502.org. In every CPU, there is a particular wire that turns on and off at a steady rate to help keep everything in sync. That wire is called the clock, and the clock in this simulation is turning on about twice a second. Modern CPUs are measured in gigahertz, giga meaning billion and hertz meaning times per second. So the clock in modern CPUs turns on several billion times per second. That speed is what allows CPUs to do very complicated things very quickly. However, what the CPU does during each clock tick is actually very simple, and something we'll look at more in this video. For now, we'll zoom back out and put the cover back on. The CPU in your computer might be manufactured by a company like Intel or AMD, but the type of CPU we're going to look at today is called the Scott CPU. The Scott CPU doesn't actually exist except as a design in a book called But How Do It Know by John Scott. The design of the Scott CPU is copyrighted and is being used in this video with John's permission. The book is available at buthowdoitknow.com. This is a great book that goes through each of the components in the CPU very slowly, without using a lot of overly technical jargon. If you've been looking for a book that explains how a computer works, I would highly recommend this one. So let's flip the CPU over and look underneath. You'll see a lot of pins sticking out that allow the CPU to take in information and send it back out. The CPU fits into what's known as the motherboard. The motherboard allows all the components in the computer to connect to each other. So we'll flip the CPU back over and plug it into the motherboard. On the right of the motherboard is a place for something called RAM. RAM is short for Random Access Memory, and it just contains all the data that is being processed by the CPU. Let's learn a little bit more about RAM by looking at how the CPU and RAM interact. For now, we'll remove the wires on the left and move the motherboard over to make room for the RAM chip. RAM consists of a list of addresses, and at each of those addresses is a piece of data. The CPU normally requests and processes each piece of data from RAM in order, one after the other. However, if the CPU is instructed to pull data out of order, it can do so. That is why it's called Random Access Memory. The data can be accessed randomly if it needs to be, although normally it's accessed in order. When the computer first starts running a program, it sends an address to RAM to begin retrieving that program. The RAM address just consists of a series of ones and zeros representing on and off wires. RAM doesn't do anything with that address, though, until the CPU also turns on the set or the enable wire. If the enable wire is turned on, RAM automatically sends whatever piece of data is at that address back to the CPU. That data is then processed by the CPU accordingly. Once the CPU is finished processing that piece of data, it then sends another address to RAM, turns on the enable wire, and gets the next piece of data from RAM. This process happens over and over again inside the computer. If the CPU needs to save data to RAM, it outputs an address, outputs some data, and then turns on the set wire. The RAM will then overwrite the data at that address with the new data. But what is that data inside RAM? Because it just looks like a bunch of ones and zeros. Well, it's made up of different things. Some of the most important pieces of data in RAM are the instructions. Instructions just tell the CPU to do different things. There are also numbers inside that data. These are numbers that you might want to add together, compare, or simply process in some way. Another thing, and this is kind of weird, that is in the data is addresses. At particular memory addresses in RAM, the data itself is also an address. These addresses can be used for various things. For instance, if you want to output a number to an external device, you have to know the address of that particular device. Do you want to send data to the printer, or do you want to send it to the monitor, for instance? There are also letters stored in RAM. If you want to show some text on the screen, you would actually store it as a bunch of ones and zeros in RAM. Each letter is stored as a particular combination of ones and zeros according to a character code. These character codes are arbitrary. Someone just decided that this is a lowercase a and this is an uppercase G, for instance. So that's what's actually in the data inside RAM. Now let's go back to seeing the data as just a bunch of ones and zeros. And we'll now move the RAM chip into the RAM socket on the motherboard. We'll then group the RAM addresses and data together, pull the CPU out of the motherboard, and look at what's called the instruction set of the CPU. As we saw earlier, some of the pieces of data in RAM are instructions, and each CPU has its own set of instructions that it understands. So there might be a load instruction, which loads a number from RAM into the CPU. After a couple of these load instructions, there might be an add instruction that adds these two numbers together. After an add instruction might be a store instruction, which saves the result of that addition back out to RAM to be used later on. There might also be a compare instruction after some load instructions, which compares two numbers together to see which one is larger or if they are the same. The compare instruction can be very useful when used in conjunction with what's called a jump if instruction. As we saw earlier, the CPU generally requests each piece of data from RAM in order one after the other. Sometimes, though, the programmer wants to jump to an out-of-order RAM address to process some other instructions in memory. The jump if instruction checks to see if a certain condition is true before it jumps. It uses the results of the compare instruction to make this decision. There is also a regular jump instruction that jumps no matter what. Finally, there is an out instruction and an in instruction. These will output data to an external device like a monitor, or input data from an external device like a keyboard. These two instructions are often used in conjunction with an address, like we talked about earlier. There are some other instructions in a CPU's instruction set, but these are some of the more commonly seen ones. So as we saw, the data in RAM consists of things like instructions, numbers, addresses, and letters. So let's go through a program that would use this instruction set to play a guessing game. So it would load a number like 9 into the CPU. Let's say that the programmer decided that that was the right answer, so he went ahead and put that number into RAM. And then comes an in instruction to retrieve the user's guess. After the in instruction is the address of the keyboard, so we can know where we're getting the data from. Next comes a compare instruction that checks to see if those two numbers, the one saved by the programmer and the one entered by the user, are the same. Following the compare instruction is a jump if equal instruction, which will jump to another address in RAM if those two numbers we just talked about are the same. The jump if equal instruction is immediately followed by a new RAM address. If the two numbers are the same, the CPU jumps to that new address to begin processing its next set of instructions from there. If the two numbers are not the same, then the computer ignores the jump if equal instruction and the corresponding address and just keeps going. Following the jump to address comes an out instruction with the address for the monitor, then the letter capital G, and then below that would be the letters U, E, S, S, space again, so guess again. So if the user guesses the wrong number, the program would tell him to guess again, and then jump back up to the in instruction to retrieve that new guess, and then process these instructions all over again. By the way, the in and out instructions used here have been simplified somewhat, but you'll find them covered in more detail in the book. So now let's briefly take a look inside the CPU itself to see how it would process an instruction. As we saw earlier, this is the inside of the 6502 CPU. Let's take away the 6502 wiring and see what's inside the Scott CPU. The first component is the control unit, which is kind of like a captain in the Army. It receives its orders from RAM in the form of an instruction, and then breaks that instruction down into specific commands for the other components. One of the most important components under the command of the control unit is the arithmetic logic unit, or ALU for short. The ALU is what performs all the mathematical operations inside the CPU, such as addition, subtraction, or even comparison like we saw earlier. The arithmetic logic unit has two inputs. We'll label them input A and input B, and assume they are two numbers from some previous load instructions. Now we might want to add those two numbers together. The control unit receives that instruction from RAM and then tells the ALU what type of operation to perform. The ALU performs the operation and then outputs the answer. Sometimes, though, depending upon the type of instruction, the output from the ALU can actually be ignored. For instance, if you have a compare instruction, the ALU doesn't need to output an answer. Instead, it just needs to tell the control unit how the two numbers compare to each other. For this, the ALU uses what are called flags, and they help the control unit decide what to do when it receives the next instruction, like jump if, which we'll see later. For now, though, let's say that we are working with an instruction that does produce an output. Where does that output actually go? Well, the 8 wires coming out of the ALU would actually run to what is called a register. A register is a very simple component whose only job is to store a number temporarily. Registers act just like RAM, except they are inside the CPU, making them faster and more useful for storing a number temporarily while an instruction is being processed. When the ALU sends the output to the register, it won't actually be saved until the control unit turns on the register's set wire. The set wire is just like the one we saw earlier for RAM. When the set wire is turned on, the register saves whatever number is on its input wires. Once we have the output saved in the register, though, how do we get it back out? Well, when we are ready to move a number out of the register, we need another control wire called the enable wire that also runs from the control unit to the register. As soon as the control unit turns the enable wire on, the register will output whatever number is saved inside. The output wires of the register then connect to what is called the CPU bus. A bus, as we saw earlier on the motherboard, is simply a group of wires that connect multiple components inside a computer. On the bus are some other registers with their own set and enable wires. These may have numbers from previous instructions already saved inside. So the control unit will then turn on the set wire of the particular register that it wants to save that number to, and that number will be saved in that register. Afterward, the control unit will then turn off the enable wire from the first register and clear the bus. The 4 registers at the top are just used for storing numbers between operations, so they have output wires that go directly back onto the bus. So now we have moved a number from one register to another just by turning some wires on and off. That's the advantage of the bus, easily moving numbers between components. The disadvantage of the bus is that you can only have one number on it at a time. Because of this limitation, the arithmetic logic unit uses a temporary register for input B. When the control unit is processing an instruction involving the ALU, it will move one of the inputs to the temporary register. The temporary register has no need for an enable wire since it only outputs to the ALU and doesn't conflict with any other registers. The other input to the ALU comes directly from the bus. The control unit will enable another register, and that number will become input A to the ALU. That number stays on the bus until the ALU is finished processing the instruction. And so now there are 2 inputs to the ALU, and we're ready for the ALU to perform an operation. As we saw earlier, the control unit knows what operation to tell the ALU to perform because of the instruction it receives from RAM. The instruction itself is in another register called the instruction register. By the way, the input wires from the bus won't affect this register since the instruction was already saved in a previous step. This register, like the temporary register, also has no need for an enable wire since it just outputs to the control unit. Based upon this instruction, the control unit then tells the ALU what type of operation to perform. So let's say the instruction we're processing is a compare instruction. With the compare instruction, we're not interested in the number that is output by the ALU. We only want to know how the 2 inputs compare to each other. For that, we use the flags that we talked about earlier. Each flag is just a wire that turns on or off depending upon whether or not a certain condition is true. Inside the Scott CPU, there are 4 flags, and we'll look at 2 of them now. The A is larger flag will turn on if input A is larger than input B. If the inputs are the same, then the equal flag turns on, and if both of these flags are off, that means input B is larger. But in this case, the equal flag is on, so that means both inputs are the same. Once the compare instruction is over, we still need to use the flags for the next instruction, so we'll save them to a register that only has 4 inputs and 4 outputs, 1 for each flag. Once the flags are set into the flags register, the CPU is finished with the compare instruction, and it can then request the next instruction from RAM. Generally, the next instruction after a compare instruction is a jump if instruction. This combination of a compare and a jump if instruction, by the way, is very common in computer programming. Anytime there is more than one possible path through a program, the computer is using these instructions to tell it which way to go. So now that we're finished with the compare instruction and our flags are saved in the flags register, we need to tell RAM that we're ready for the next piece of data, in this case the next instruction. So inside the CPU, another register that is very important is what's called the instruction address register. The CPU uses this register to know where the next instruction should come from in RAM. When the CPU is ready for the next instruction, it enables the instruction address register onto the bus. Eventually, the instruction address will flow to RAM, but it doesn't get there directly. There is an intermediary register called the memory address register, whose only job is to tell RAM what memory address the CPU wants next, since it won't always be an instruction. Once the instruction address is set into the memory address register, it is automatically sent to RAM, since the memory address register doesn't have an enable wire. The control unit then turns on the enable RAM wire, and RAM automatically sends back the data at that address, which in this case is an instruction. That instruction is then saved in the instruction register, and the control unit begins processing it. In this case, it's a jump if equal instruction, which checks to see if the equal flag is on. It does that by running one of its wires and the equal flag wire into an AND gate. If both inputs to the AND gate are on, then the output wire turns on as well. This output wire will then trigger the jump. That jump eventually retrieves the next piece of data from RAM, which happens to be an address, and move it into the instruction address register. When the jump if equal instruction is over, the CPU then processes the instruction at that new address. At that new address may be some instructions that output the text "you guessed correctly" onto the screen, because now we know that the user guessed correctly. So we'll add the final 4 wires to our CPU, which are used to control the external devices like the monitor and the keyboard. We now have a nearly complete picture of what the Scott CPU looks like. Data moves around inside the CPU using the bus and is stored in each register according to how that data is going to be used. Each instruction that we have seen can be processed by the Scott CPU in about 6 clock ticks. Modern CPUs can process multiple instructions per clock tick, meaning that the computer you're using to watch this video is likely processing tens or even hundreds of billions of instructions per second. That phenomenal speed is accomplished by using more than one of each component and making sure that all the components are active as much as possible. This makes modern CPUs much more complicated than the Scott CPU, but they are still fundamentally doing the same things as the Scott CPU. So now let's zoom back out and we can see all the wires that run back out to the pins on the chip. On the right are the set RAM and enable RAM wires. On the top are the RAM address wires. On the bottom are the data wires that run to both RAM and the external devices. And on the left are the input-output control wires. So let's zoom back out to see the rest of the chip, and we'll put the cover back on the CPU and put it back in the motherboard. Using the ports on the left, we can now plug in the cables that connect our monitor and our keyboard. Each of these ports has an address, and that port address is what the CPU uses with an in or an out instruction. That port address, by the way, is sent using the data bus, since the address bus in this computer is only used for RAM. So we'll zoom out to see how the motherboard fits inside the computer case. In the computer case is the last component we'll look at, which is the hard drive. As soon as the power to the computer is turned off, all the data in RAM is lost, so you have to have a way to store it more permanently. For that, we use a hard drive. Inside the hard drive is a spinning disk covered in tiny magnets with a small metal arm floating above it. The arm moves around to the different parts of the disk where different data can be stored and retrieved. The disk and the arm generally move very, very quickly, but nowhere near as fast as the CPU can process data. For this reason, all the data from the hard drive must first be moved to RAM before it can be processed. So we'll put the hard drive back inside the computer and zoom out. Here we can see the program we just ran and the message telling the user that he guessed correctly. So now you've seen the very basics of how a computer...
We know that CPU is faster compared to main memory, and as main memory is faster compared to secondary memory, the hard disk, but then main memory is not as fast as CPU. So see this, assume that we have CPU and consider the architecture where CPU wants to read something. If CPU has to execute something, it has to read something from main memory and then execute it. Then the speed of the CPU is obviously limited by the speed of the main memory. In some sense, you could say like this: in order to execute an instruction, CPU might take, I'm just assuming this, okay? In order to execute an instruction, CPU might take 10 power minus 12 seconds, okay? But the instructions are present in main memory, right? So now instructions, in order to fetch something from main memory, in order to read something from main memory, it might take 10 power minus 9 seconds, right? And maybe there is a hard disk, this secondary memory, sorry, following it. So CPUs, are able to execute very fast, but then main memory will not be able to give the CPU instructions at that rate. Then what happens? The speed of the CPU will obviously fall down to the speed of the main memory. Now, why is this delay? Because in order to get a word from main memory, we have to go on to the bus. There is something called as bus. We shall see it later. But anyway, then we have to go on to the bus, that is set of wires, and then get something from this, right? So in order to avoid this, what we generally do is we use some speed memory devices or speed memory storages. So one such storage is registers. So on the chip itself, on the chip in which CPU is present, if we have the registers, now these registers, since they are present along with the CPU on the same chip, they will be very fast compared to the main memory. And in case if the instruction is prefetched means before executing itself, if the instruction is present, if the instruction is present in this registers, then CPU can get it fast and execute it faster, right? So that this solution is fine, it works. But the problem is register size is too small. In the sense, registers will not be able to hold the entire program. They will be able to hold only few instructions because they are costly, right? And then there is a trade-off. Then what we did is, then many people, the designers, they invented this new device called as cache. So cache is a high-speed memory which is not as costly as the registers, but it is faster compared to main memory. So cost-wise it is cheaper, fast-wise it is better, right? Therefore, if we have something, if we have a program, at least a part of it, the process which is present in the main memory, if at least a part of it is present in cache, then CPU will be able to get the instructions fast and execute it faster, right? So now if you watch it, we are not just using one level of memory, we are having various levels of memories, right? So CPU is having registers, that is level 1, and then cache level 2, and then main memory, and then secondary memory. Like this you can have any number of levels. Sometimes what people do is they'll even have one more level of cache, right? So that cache will be cheaper compared to this cache, but it will be slower compared to this cache, which means you can have level 1, level 2, level 3, level 4, any levels of hierarchy, right? By using this hierarchy, what is the advantage we get is the overall system cost will not be as high as the maximum cost memory element. It is actually normalized, right? If you want to understand it in other way, like see this, a process will be present in the secondary memory, that is called virtual memory concept. And now a part of the secondary memory process will be present in main memory. Let us say we are using paging, got it? And now a part of the page will be now present in the cache, right? And a part of the cache will now be present in registers, right? So CPU, if it wants anything, it will first look into registers. If it is not present, look into the cache. If it is not present, look into the paging, and if it is not present, look into the secondary memory, right? And now if the required element is present directly in the cache, okay, let's forget about registers, because the time taken to look into the registers and get something in registers is negligible. So let's not talk about registers. Let's say we have 3 levels of memories. First level is cache, second level is paging, the main memory, and the third level is secondary memory, right? So whenever we look into the cache and we are able to find out, if we are able to see that whatever we require is present in the cache, that is called as cache hit. Cache hit. So cache hit is if the required element is present in the cache, that is called cache hit. And the time taken to find out whether it is present in the cache or not, that is called as hit latency. Hit latency is time taken to find out whether whether the required element is present in the cache or not. In case if the required element is not, either it could be instruction or data, if the required element is not present in the cache, it is called as cache miss. Cache miss means the required element is not there. And Now in order to get the required element, we have to go to the main memory and then fetch it and then read it, right? And that is called as miss latency, the time taken to get something from the main memory and then place it into the service this cache and then get it, right? So hit latency is cache hit depends on various factors, and cache miss also depends on various factors. Okay, so what is cache hit and cache miss is whenever we refer to something, whether it is going to be present in the cache or it is not going to be present, and that particular thing depends on various factors. One factor is, okay, we shall see all the factors later, right? And next thing is, if the required thing, if whatever you are looking for, the element, if it is present in main memory, right, that is called as hit. In case if it is not present in main memory, that is called as page fault, isn't it? So there also we had something called as page hit and page fault, right? So how do we find out whether what is the page hit, whether it is a page hit or page fault? We have something called as page tables. So using page tables, we are able to find out whether the required element is present here or not. But then how can we find out whether the required element is present in cache or not? For that reason, exactly the same column, exactly like how we use the paging concept and then the page table, we are going to use here something called as tag directory. Tag directory. You can somehow compare it to the page table of the paging. I mean, there is difference, but then semantically they are same. In the sense, page table says whether a required page is present in the main memory or not. Similarly, the tag directory says whether the required element, right? I'll tell you the terminology slowly later. This tag directory says whether the required element is present in the tag or not, right? So before you access the main memory, you are accessing the page table, right? Similarly, before you access the cache, we have to access the tags. Once we look in the tags and find out that the element is present, then we are going to get into the tag and take that element. Got it? Okay. And now in this case, whenever there is a page fault, we are going to do something called as service, that is called as page fault service time. What is page fault service? Get the page from the secondary memory and then load it here. Got it? So if you want your access to be very, very fast, I mean your CPU to run very fast, see that whatever you are looking for is going to be present in the high speed memory, that is level 1. In case if there is a miss, see that it is at least present here. In case if it is a miss here, then your program is going to be as slow as this secondary memory. Got it? So finally our aim is to see that we have to get the information into the highest high speed memory and store it there, and then we should be able to access it, and in case if it is not there, we should be able to go to the next level and get it. So the entire cache memory, the entire purpose is to reduce the cost of the system, because we cannot directly base on registers, right? That is why it is reducing the cost as well as increasing the speed of the CPU better than the main memory, which means without cache, whatever was the speed, if we introduce cache, even though cost is going to increase, but the speed is also going to increase, right? And now we have to talk about various things here. How are you going to see, one thing is for sure, always cache memory size is going to be less than the main memory size. Then various factors will come into picture. If you have the capacity to load only a part of main memory, which part are you going to give priority to, isn't it? Then there is something called as locality of reference. Locality of reference says that there are two types of locality of reference. One is called as spatial locality and other is called as temporal locality. Spatial locality says that whenever you are looking for any element, the chances are that that particular element will be present in a close proximity around the one which we have previously referred, which means in a program, let us say you have a program like this, many lines, and now if you are referring to a particular element, there is a chance that this element will be in a close proximity to earlier reference, right? Or in case if you are referring to some element here, then the chances are that next time the next reference will be close to this reference. That is called as spatial locality, and other is called as temporal. Temporal says that least recently used element is going to be used again. That is why in the page replacement the most frequently used algorithm is least recently used. So LRU actually takes care of temporal locality. Temporal locality means in time whatever was latest referred, the last referred, last recently used, then that is going to be used again. That says that is temporal. So LRU, the algorithm LRU takes care of temporal locality, and the block, having block sizes or page sizes, these pages. I think you understood why we always see whenever there is a page fault. I think you remember this. Whenever there is a page fault, we are not just going to get that particular word which is required inside the page. Even though only one word is required inside the page, we are actually fetching the entire page from the secondary memory. Why are we doing this? Because we want to even follow that law of spatial locality of reference. Spatial locality of reference says that if you are referring to a word, particular word, then the chances are that next time you will refer to some word around it. That is what spatial locality says. And temporal locality says that if you are referring, the chances next time the chances are greater that the least recently used word is going to be used. That is why LRU will take care of temporal locality and block size will take care of spatial locality. Got it? So that is why we generally load in blocks. Even though one word is required, we generally don't load only one word, right? So now what happens, as you increase the size of the block, you are increasing the you are following more the law of spatial locality, right? Okay, fine. We shall see this topic again in another topic. I'll just leave it to other day. But then now we shall focus on some other topics here. The main focus will be on this topic. How are you going to get the part of the main memory into the cache, and how are you going to keep track of what is present in the cache, and next whenever the cache is full, which one are you going to replace so that you can get the new part. So this is what my focus is. So if you can answer all these questions, then caching is over, right? So entire caching is main questions on caching will contain numerical questions. We shall see all the models, okay? And now I recommend that it is not a compulsory thing, but then if you are watching it, I really recommend that you please watch the paging section of operating systems and then come back. You'll understand it better. Okay, but then it is not absolutely needed, but I really suggest that you do it. Okay, otherwise you can continue with this also. If you are interested in caching first, yes, you can continue with this, but then please visit, if you have time, you please visit operating systems paging and then come here. Okay, because it will make some things easy, especially the numericals easy and calculations will be easy for you. Fine.
One of the most important components inside of your computer is the memory. We often refer to this as RAM. That stands for Random Access Memory. And that really is the most common type of memory inside of our computers. When we talk about how much memory is inside of your computer and should you be getting a memory upgrade, we're often talking about random access memory as the memory type that we are changing. This is not referring to the storage device that you have in your computer. You probably have a hard drive or even these days SSD, which is a type of memory, but it's designed to store data over a very long period of time. And when we talk about how much memory is inside of your computer, we're talking about the RAM. We're not talking about the permanent storage space that might be inside of your computer. The reason that this RAM is so important is that inside of your computer, nothing happens unless you are executing a program that exists in this random access memory. So all of these applications and programs that you're using will only work if you've moved them off of your storage device, placed them into random access memory so that you can then use a spreadsheet, do some word processing, or surf the internet. Another type of memory inside of your computer is a very specialized type of memory called a ROM. It stands for read-only memory. These are memory chips that are inside of your computer that are not going to ever change, as the name implies, with read only. We are only going to be able to read the information from this memory. We are not going to be able to change the information inside of this memory. So this is a great place for the BIOS that's used to start your computer. That way nothing can ever delete the BIOS. It's always going to be in this read-only memory. There are different kinds of read-only memory. One kind is a PROM, that stands for Programmable Read-Only Memory. This is where an engineer might write code to a chip one time and place that chip inside of your computer. So it is a read-only memory that is initially programmable. We also have an EEPROM. This allows us to take that programmability of the read-only memory and erase everything and write over it. So we're able to pull that chip out of the computer, put it into another device where we can effectively reprogram it and then put it back into your computer again. Obviously, these would be used for very unique purposes. We don't often use these EEPROMs inside of our computers because we're not often pulling the ROM out and making changes to it. One type that is inside of our computer, though, is an EEPROM that stands for Electrically Erasable Programmable Read-Only Memory. So if you have flash memory, if you're using an SSD inside of your computer, if your BIOS is one that you can upgrade with a software program, it's probably writing it to EEPROM, which allows us at any time to electronically erase it and write anything else into that read-only memory. There's a very specialized kind of RAM inside of your computer called a static RAM. You may see this abbreviated as SRAM. This is very fast memory. It's used for some very specific purposes inside of your computer. Because it is so fast, it's also much more expensive than the traditional random access memory that we would use on the memory sticks inside of our computer. It's also relatively large when you compare it to that other type of random access memory. So it takes up a lot of room, a lot of real estate inside of your computer relative to the other memory types. Because this is so fast, though, we often will see it used on the CPU itself or just off the CPU as processor caches. You may see this referred to as level 1, level 2, or level 3 caches, abbreviated as L1, L2, and L3. The static, when we're looking at the memory requirements for an operating system or describing how much memory we have inside of our computer, we're really talking about the dynamic random access memory that's inside of our computer. This memory is called dynamic because we are always refreshing the contents of this memory. So there's always a refresh process that goes through this memory constantly so that it doesn't lose any of the information. That's different than the static RAM we were just talking about that didn't require the constant refresh. With our dynamic RAM, we'll always be refreshing and updating the information inside of that memory. This is also random access memory, which means we can put information anywhere on these memory chips and instantly access that information just by referencing a particular memory address. It makes it very quick to retrieve and put information into the memory. It's very different than if you were using a backup tape drive with magnetic tape, where you have to fast forward or rewind through the tape to find exactly the place where that information is stored. Because this is randomly accessed, we can simply ask for a particular address and instantly grab the information that's stored in that memory. We talked earlier about the dynamic random access memory. This is synchronous dynamic random access memory, and it's called synchronous because it is synchronized to a common system clock. You can think of this computer constantly ticking off the seconds, and every second there's a particular process that's occurring. Obviously, inside of our computers, there are many millions of processes that are occurring every second, but because it is synchronized to a clock, all of the other components inside of the computer know exactly what's going to be happening with the next tick of that clock as it goes by. We used to have the dynamic random access memory that was not synchronous, which means that there was no clock signal. The memory was simply accessed whenever the system would have availability. With this SDRAM, we need to make sure that we don't confuse that term for the SRAM that we were looking at earlier, which is the static RAM. So whenever we're putting more memory inside of our computer with an extra memory module, we're always going to be referring to an SDRAM module. Let's visually look at this single data rate and how it is synchronized with the clock that's inside of our computer. Let's look first at the clock signal itself. You can see there's an upper and lower as the clock is rising and falling on each individual clock cycle inside of your computer. So we have 1 clock cycle, 2, 3, 4, 5, and 6 total clock cycles on this particular diagram. And you can see with each clock cycle, we're able to transfer one piece of data. So if the first clock cycle is the first data, the second clock cycle, then we've got data number 2, the third clock cycle, data number 3, and so on. That's one significant characteristic of the single data rate is for every single clock cycle, there is a single piece of data. The type of memory that you'll find in today's computers is DDR memory. This stands for double data rate. As the name implies, it is twice as fast as the single data rate memory was. That's because we're able to both send data on the rising and the falling of the clock. So effectively, we can send twice as much information at exactly the same clock time. So we didn't have to change the clock speed of the memory. We simply changed how we were sending the information during that same clock period. If you were to look at a DDR module, you'll see that it has about 184 pins on the memory module itself. In the industry, there's an interesting naming convention to memory. We can describe memory as the total number of transfers that it can do in a single second, but we might also describe the memory as the total throughput available for the memory. If we're talking about a memory module and the total amount of transfers that it can do in a single second, then you'll see it described as DDR- the number. So DDR 200 means that this memory can do 200 million transfers in a single second. To be able to describe this memory as total throughput, we simply multiply that DDR number 200 by the number 8, and we get a total of 1600, and we put the term PC in front of it to describe the total throughput. So a DDR 200 has exactly the same throughput as a PC 1600. We're just describing this throughput in two different ways. If we were to put a single data rate memory and the double data rate memory side by side, you would see what those differences are in the total amount of information that was transferred. As you recall, with the SDR, we had a single clock cycle and we were able to send one piece of data. But with DDR, you've got double data rate. You can have a single clock cycle, but you're sending data on the high end of the clock and the low end of the clock, which effectively is doubling the amount of throughput over an SDR. If we were to drill down into the statistics associated with DDR memory, you could see the memory clock speed is here. That's referring to how fast the clock is inside of the memory itself. You've got the I/O bus clock speed. That's how fast the bus is outside of the memory, whatever the memory is connecting to. You also have the DDR speed. We mentioned earlier the DDR 200. That's describing how many transfers you can do in a single second. I've broken that out as a separate column just so you're clear that a DDR 200 is 200 million transfers in a second. And of course, if we multiply that times 8, we'll get the total transfer rate in megabytes per second. So a DDR 200 multiplied by 8 gives us 1600, which means the module name is called PC 1600. We can do a similar thing if the memory clock speed is 200. That means the I/O bus clock speed for DDR memory is also 200. But again, it's going twice as fast as the clock rate, which means we have a total of 400 million transfers per second. So we call this DDR 400. Multiply that times 8, you get 3200, which means that our module name is going to be PC 3200. So that's a very easy way to change the module name back to DDR speed, is to simply multiply by 8 to get the module name or divide by 8 to get the DDR speed. DDR memory was certainly an improvement over SDR because we were able to get twice the throughput of SDR, but we needed to go faster. Our faster processors and faster computers required much more throughput, so we came up with the next generation of DDR memory called DDR2, or double data rate 2. This is twice as fast as the DDR memory that was previous. You find these memory modules are 240 pin memory modules as well. These newer DDR2 modules were not backwards compatible with the older DDR motherboards, so you couldn't grab your DDR2 module and put it into an older motherboard that was expecting a DDR memory module. You have to make sure that you're using exactly the right kind of module for your motherboard. Because of the architecture of DDR2, we're able to transfer twice as much information without changing the clock speed of the memory module. So a memory module that's 100 megahertz with DDR2 would need an I/O bus clock speed of 200 megahertz because it was transferring twice as much information over that bus. And of course, since it's double data rate memory, it would be twice that amount, or DDR2 400. And you can see DDR2 specifies that we're talking about DDR2 memory. That's 400 million transfers per second. And if we use our equation to multiply that by 8 to get the transfer rate, that means that we would be transferring 3,200 megabytes per second. And because this is DDR2 memory, we refer to it with the name PC2 3200 rather than the PC term that we would use with DDR memory. So if you ever see a number that's next to the PC or the number that's next to DDR, you'll know that you're dealing with regular DDR memory or with DDR2. The next generation of DDR is called DDR3. This is an improvement over DDR2. In fact, this goes twice as fast as DDR2 memory while maintaining the same clock rate inside of the memory chips. We're also able to get much larger memory capacities out of DDR3, and this also has 240 pins, which is exactly the same as what we saw with the DDR2. As with the previous memory types, this DDR3 memory is not backwards compatible. If you have a motherboard that is expecting DDR2 memory, you cannot put DDR3 memory modules. It simply physically won't fit in the computer. But even if it did, these two memory module types work completely different and they would not be compatible. With the DDR3, everything is now moving twice as fast as DDR2. So we might still have the same 100 megahertz memory clock speed, but now the I/O bus is needing to be 400 megahertz because we have now doubled that over DDR2. And of course, since it's DDR, we are now transferring 800 million transfers per second using that 100 megahertz memory clock speed. And we describe this as DDR3 800. Again, we multiply by 8 and we get the total transfer rate in megabytes per second. So for DDR3 800, multiplied by 8 gets us a module name of PC3 6400. So let's now look at DDR, DDR2, and DDR3 right next to each other. You can see the DDR, DDR2, and DDR3 examples I'm using here are all using the same memory clock speed of 100 megahertz. But notice that the I/O bus clock speed is identical with DDR. It's doubled for DDR2 and then doubled again for DDR3. So our 100 megahertz clock speed has a DDR speed of DDR 200, DDR2 400, and DDR3 800. And of course, with each of these numbers, we multiply by 8 to get the transfer rate that we use for the module name. And of course, remember that our module names are numbered. So with the DDR memory, it's a PC 1600. With DDR2 memory, it's a PC2 for DDR2. 3200, and then for DDR3, it's described as PC3 6400. I mentioned earlier that these DDR types were not backwards compatible, and not only do they work differently inside of the memory itself, but the physical chips are designed to be different, and they're designed this way so that we can't make a mistake by putting the wrong memory module in a different slot. You can see there are notches in the memory module, and these notches are at a very certain spot. So DDR memory, you can see where the notch is. For DDR2, it's moved a little bit over. For DDR3, it's moved over even further. So you can find the memory modules that seem to be the same dimensions. They're the same length, they're the same width, but you'll find when you get to your motherboard, you may not be able to put it into the motherboard itself because there's a notch that's inside of there that won't allow the wrong memory type to be installed on the motherboard. And it works exactly the same if you have a laptop that's using SODIMMs. Same scenario, you have notches on the SODIMMs that are marked so that you're not able to put the wrong memory type into a different memory slot.
Hi, I'm Jack Buffington for RobotBrigade.com. This is another video in my series of videos about digital logic. In this one, I'm going to talk about ROMs, or read-only memories. And a ROM is a logic device that you can use as a lookup table or as a place to store. It's often used as a place to store your program for a microprocessor or a microcontroller. And it is just a combinational circuit that you put an address in and you get data out. And the way that a ROM works, and this is a very simplified version here first, is here's a decoder. All right, and I'm just going to do a 2 to 4 decoder. And let's say that this is a 4-bit ROM. All right, so a ROM is not user configurable. You have to send a ROM table to the factory and have them actually make this in silicon. So this is only used if you are going into very high production, because the cost of having a ROM made is pretty darn high. So you want to make sure that your program is completely bulletproof, or whatever you're looking up out of this ROM, before you have it made. So before this, you'd be programming with an EEPROM or an E. Nobody really uses EEPROM anymore. Anyway, so the way that these work is you have little diodes like that everywhere that a bit is a 1. Actually, I should draw these here. These are resistors. Okay, and then we have, because this is such a weak signal, and I'll just draw a couple other, these would be diodes. Because these are such weak signals, we have output buffers. Not all ROMs use diodes. They might use a transistor or something like that. But from this, you pretty much get the idea. So this is what is called a one-dimensional ROM. And there is another more commonly used format, and that is called a two-dimensional ROM. Now what I'm going to draw here is a 1-bit output ROM. And if you were going to have multi-bits, let's say an 8-bit, you would just have to have 8 of these circuits. So the first thing I'm going to do is I'm going to start out with a decoder again. All right. And so this is like address 0 and address 1. And then down here, I have a multiplexer. And depending on what your logic is, this could be any number of inputs, and this would be your address 2, address 3. And so, just like the previous one, there's a bunch of connections. It's only 2 inputs, so we can only have 4 of these. And anyway, you have your diodes connecting stuff up like that. And here is your output. So here we have 4 address bits, which allows us to select one of 16 connections over here, and we get our bit out. And if we wanted to have a multi-bit one, well, then we just run the addresses into an exactly identical one, except for the connections are different, to give us data for another output. So that's ROMs. ROMs are used, unlike the programmable array logic and programmable logic array. ROMs are still used because if you are going into high volume, they are very cheap. And so you'll see this in everything from little toys that have sounds encoded into them to maybe in your DVD player, the boot ROM will be that. You typically won't find it for your BIOS in your computer. That would be generally a flash ROM or EEPROM.